For a while, I was getting a lot of YouTube videos popping up of people hanging onto a ladder or standing on a ladder, and then the ladder tips over and falls with the person on it. So once I started looking into that on the physics and how hard they were hitting the ground, I stumbled across what I think is a paradox and a problem that leads to a lot of answers that I think is really interesting. Or I guess you could say this problem leads to a lot of questions that have a lot of answers. But you got to dig deep for those answers. And as usual, that's what I did. So this video would be appreciated by somebody that's had their first semester of trig, first semester of calc, first semester of physics, and they want to know how to apply all this information, possibly to answer a real-world question or a real-world problem that if you understand it, then someday it could save you from getting injured. And also granted, some of those people falling on ladders may have been AI. The best AI videos are the ones that copy real life scenarios, so it makes it more believable. But either way, it poses an interesting question, or actually a lot of interesting questions. Okay, so why do we need radians and not degrees? Because I know as a trig student, I think most people hated radians, didn't really understand them. We always preferred degrees because everybody knows what 90 degrees is or 180 degrees. But we have to use these radians to get the area under the curve. Why would you want to do that? How do you do that? I'm going to answer that here. And then here's the paradox. Like I said, you'll need some calc, trig, and physics to understand it most likely. I've done several videos on other paradoxes as well. The one video was just called Paradoxes and had several paradoxes in it. Another was on the boy-girl paradox. So you can see those if you're interested. But here's another thought. It's good to be metacognitive, which I guess you could describe as not just thinking about something, but thinking about why you're thinking about it. So for example, I'm thinking about a paradox right here, but then again, some people may argue that there are actually no paradoxes because if you get a problem wrong with math or physics, then that just means you didn't understand the math or physics. But I think a paradox is a good descriptive term to describe something that has a deeper level of complexity where your initial assumption is different than what the math shows. So at any rate, I'll show the next page. Okay, so here's the question, or here's the scenario. You got three people on top of a tall cliff or building or something, and or maybe it's the same person and they have three ways to get down. So they could just jump and free fall, or if they have a pole here, they can grab onto it and pole vault down, or if they have a slide, and let's say this is a slide in the wintertime, so there was an ice storm, and the slide is covered in ice, so that it's frictionless, and they slide down this slide. But somebody parked a big truck or a car right at the bottom of that ramp, so when they slide down it, they're going to run into that car. So here's the question. Which one of these scenarios leads to the greatest impact and requires the greatest amount of padding to prevent injury? Which one leads to the second greatest impact, and which one leads to the least amount of impact or the safest way to go down? And I drew some what looks like maybe cardboard boxes here because I saw on TV they said that sometimes with movies, if they want to do low budget falls or stunts, they can just use cardboard boxes for people to fall onto them. So this pole vaulting scenario right here, that reminds me of the people falling while they're on a ladder and the ladder tips over. But there's also a competition in some other country where people run off of a tall ledge and grab onto a pole and then pole vault across a body of water or a canal, and they land in some soft sand, and the competition is to see who can get the farthest or achieve the farthest distance in the X direction. So here's what I think is interesting. I think normally you'd think if you were sliding down something or pole vaulting down, anything would be better than free fall, but it turns out they all lead to the same impact, which means they all hit the ground or hit the surface with the same amount of kinetic energy and have the same risk of injury. The situation here of, say, the slide going down and the pole vault, they're pretty similar because they're not going directly down, they're going down at an angle. And the slide seems like it would be the safest because normally you don't have something at the bottom and it just curves at the bottom. So that person can use all that potential energy that they have from being on top of the building that gets turned into kinetic energy, but instead of the kinetic energy going directly into the ground, it just goes horizontally in the X direction until friction slows them down. But in this case, they have a car or something here they're going to hit, which means they're going to hit with the same impact as if somebody just jumps off as a free fall. And then same thing with this pole vaulting here. It's kind of like a slide, but that slide goes down and they hit the ground here at a 90-degree angle. So all that potential energy gets turned into kinetic energy, and it's the same impact. So I'll show the math on all this. So here's the question using the basic trig, calculus, physics. We need to find the total acceleration. What this will do then, we can use total acceleration to get the average acceleration and the final velocity in the y direction. This determines how hard they hit the surface. Once you get your average acceleration, then you can find out your time in the air, just to help better understand the problem. And here's an explanation, I think, of the paradox on how the slide and the pole vaulting leads to the same impact. They will have decreased acceleration in the y direction on average, because anytime you're going down a hill, you're going to accelerate slower than if you just free fall. So they have lower acceleration in the y direction. However, this acceleration is slower, but they're accelerating for a longer period of time. This person on the slide is going to be on that slide longer than the person that free falls. The same thing with the pole vaulting. They're going to be following the circumference of this circle, and they're going to be in the air longer than the person that free falls. So the increased time and the increased distance that they're traveling will make up for that lower acceleration, so they actually hit the ground with the same impact. Also, in other words, the potential energy they have from being up above the ground, that gets turned into kinetic energy, and they have to equal each other. And that kinetic energy is what determines your velocity, your final velocity. If you have, say, a marble or a ball rolling down a ramp right here, if that ramp did what most ramps do and they smooth out and go horizontal, then all of that potential energy will be turned into a horizontal kinetic energy, so you wouldn't be hurt. And you'll have the same final velocity, but it'll be pointed in the X direction where you can slow down gradually. But if this ball takes a sharp curve right here, right before it gets to the ground, and this pipe or tube spits the ball out right here on the surface at 90 degrees, then that ball will hit the ground with the same impact as if it was just a free fall. So it will have a lower average acceleration, but it's accelerating over a longer distance and a longer period of time. And right here, I'm going to do a quick sort of tangent to explain why we have to use radians and we can't use degrees, and what a radian is. So I think most people know that 180 degrees is a straight line. So you take that diameter, multiply it times pi, and it will have the length of the circumference of the circle. I did a video on how to drive that. You can see it if you're interested. So the diameter will stretch around the circumference pi times. Radius is half the diameter, so therefore it's going to take 2 pi times twice as much to get all the way around. So halfway around will just be pi. So the circumference is measured in radiuses and not in diameters. The circumference will actually be 2 pi. So radians actually measure distance primarily. They don't really measure the angle, but you can turn it into an angle, because as you can see, if you lay your radius out here, here's where the radius would go, 1 radius, because radius is 1. So this is 1 radius, then 2 radius would be over here. There's pi radius. So you just take 3.14, multiply it by your radius, which in this case is 1. So 180 degrees equals pi radiuses, or you could say pi radians. So what we're doing is taking the length of the circumference, turning that into units of radiuses instead of meters or feet or whatever. We're turning it into a unit of radius, and then we turn that into an angle. And next page. We can take 1 radius right there, which has a unit of 1. Pi radians equals 180 degrees. The radians are the units, they cancel out. 180 divided by pi equals 57.3 degrees. So therefore, if you take your radius, lay it out over the circumference, it will form an angle right here, 57.3 degrees with rounding. So I think it's most helpful to imagine radius is actually a term of length more than a term of an angle. And the distance from here to here is 1 radius, or you could say 1 unit. And if your radius is in meters or whatever, then you'd say it's 1 meter. All right, so here's why we need radian the distance and not radian the angle. This is why we can't use degrees. I'm going to show a picture here of the person that's pole vaulting, or say they're on a ladder that's completely vertical. As that person falls down right here, their acceleration towards the ground is proportional to the cosine of the angle. So when that pole or that ladder, say, is horizontal, you're going to have maximum acceleration. You can just imagine a stick right here with a hinge or a pivot on one end, and you drop it, it will accelerate towards the ground with maximum acceleration. If that stick or that ladder is at 90 degrees, you have no acceleration. The person just hangs on to it. So it starts out with no acceleration, then its acceleration in the y direction increases as that stick or ladder falls, or as that pole vault falls. So what we need to do is get the average cosine, because the cosine determines the acceleration. We need the average cosine all along here to find out what their average acceleration is. But in order to get the average acceleration, we have to get the total acceleration. So here's what we do. We take the length of our radius right here, and we put this on an x-axis. That's how we get from 0 to pi over 2 right here. So this is actually, I think when most people are in trig, they think of this as an angle between 0 to pi over 2, but that's actually a length right here. If you have a radius of 1 meter, then you simply take 1 times pi over 2. Pi divided by 2 is literally 3.14 divided by 2, and that gives you the length right there. So what we're doing is taking the length of our circumference and laying it out over the x-axis, and we're turning that length, instead of units of meters or feet, we're turning that length into units of radiuses or radii. Then for our y-axis, we need to chart or record what the cosine value is. So when you have cosine of 0 degrees, you're going to have 1, so 1 will be on your y-axis. Cosine of 90 degrees, pi over 2 right there, that's going to be 0. So your y-axis will have 0, and it forms your sine or your cosine wave. In this case, it's a cosine wave. So to get our total acceleration, what we do is divide our length right up here into slivers. If you want to, just for simplicity, you could turn this into like 1 degree little slivers, or 1 degree little columns. So you take a cosine of 0 times 1/90th, because it is 1/90th of the length across the x-axis. Then you take, add that to cosine of 1 degrees times 1/90th, and then add that to cosine of 2 degrees times 1/90th, because we have our x-axis divided up into 90 units. But if you want to make it more accurate, you could divide it up into 1,000 units or 1,000,000 units, and you'll get increased accuracy for the area under this curve. So that's just what I said here. You add them all up, you get your total area under the curve, which means this will give you your total acceleration. And here's why we need the total acceleration, or the area under the curve, because we need that to get the average acceleration. So one way to get average acceleration is you can simply take cosine of 0 degrees plus cosine of 1 degrees plus cosine of 2 degrees. Simply just add all those up and divide by your total. Or if you want to make it simpler, you could do it every 5 or 10 degrees. I did it by 5 degrees once, just to see what I would get, and it was before I understood the whole integral thing. I took cos of 0 plus cos 5 plus cos 10 plus cos 15 all the way up to 90 degrees, divided by my total numbers there, and then I was able to get an average cosine value, which gave me the average acceleration. But a more sophisticated way to do this is you integrate all those little columns together. And so I got right here, I have my cosine wave starting from 0 degrees to pi over 2. And then I'm going to do what I think the best analogy here is a Play-Doh theory, or a Play-Doh model, where you have some Play-Doh that's in a somewhat two-dimensional aquarium or a tank. And that Play-Doh goes from a high point here down the hill to a low point. What you can do is smash that Play-Doh down, so the high part comes down, the low part comes up, and then we will get an average height right there. And that average height will be our average cosine value, which also means it's our average acceleration, so we can find out how hard these people are hitting the ground. So right here, this is why we have to have radians as a distance and not radian as an angle, because once we smash this hill down right here, our cosine wave down to get the average, we create a rectangle. We want the area of that rectangle, which means we need base times height. and that will equal area. So you can't take an angle times height or an angle times a length. That just doesn't make sense. You have to take length times length. And that's why we have to have radians as a length. So we do this to get the area under the curve, which equals the total acceleration. And then we can use that with base times height equals area to get the average acceleration. And I'll show how to do that. And next page. The integral of cos theta d theta evaluated from pi over 2 to 0 gives you the area under the curve, which also equals your total acceleration. Cos theta d theta equals sine theta evaluated from pi over 2 to 0. By the way, I cannot derive that. I just have to look at it. I wish I could drive it. Maybe I'll figure it out someday. But in the meantime, I'll just use it. Okay, so sine theta evaluated from pi over 2 to 0 equals the area under the curve, which is total acceleration. That means sine of pi over 2 minus sine of 0 gives you the area. Area will equal 1. The important thing here is when you get that 1, that equals 100% of the acceleration. This means you hit the ground with full force. Unless your slide just curves down gradually and goes into the x direction, so you can slow down gradually, which is friction. But what this shows right here is that if somebody goes down a slide and runs into a truck at the bottom of that slide, if it's a frictionless icy slide, or if somebody pole vaults down, like in that competition where people are running off of a ledge and grabbing onto a pole and pole vaulting over a canal, they're hitting the sand on the other side as if with the same force as if they just jumped off that ledge. But actually there's some dynamics there that changes things. I've seen when they run off those ledges and grab the pole, they actually climb up to the top of the pole. That actually increases their potential energy, which will increase their kinetic energy, which means they hit the ground harder. If they make it to the top of that pole while the pole's vertical, they'll have the most potential energy and hit the ground the hardest. But most of the time, they reach the top of the pole right before the pole hits the ground. So then they're not going to have quite as much energy when they hit. So just some interesting things to think about, I think. I think it's really neat to look at people in real situations or look and see what athletes are doing and be able to assess it and, I don't know, assess their impacts and their injuries. So anyways, now that we have the area, we can do base times height equals area. So area divided by base equals your height. We've taken our cosine wave, smashed it down into a rectangle. The length is between 0 to pi over 2, and we want the height. So base times height's area. Area divided by base equals your height. So height will give us our average acceleration. 1 divided by pi over 2 as the distance, not the angle. 1 divided by pi over 2, just simply the inverse of 2 over pi, which equals approximately 64% or 0.64. For the most part, I'm going to try to leave this as 2 over pi because that's more accurate. That 0.64 is a rounding number. All right, next page. Actually, before I go to the next page, what this means, average acceleration is 64%. I think another paradox that I actually fell for this, or I got this wrong when I was looking into this initially. I thought this meant with only 64% of the acceleration, they're only going to be falling as if they fell from 64% of the height, but that is not true. Because as I showed earlier, they have less acceleration in the y direction, but they make up for that by traveling over a longer distance. Okay, next page. So I think this subject's really interesting because it's actually paradoxes within paradoxes. If somebody looks at a situation of somebody pole vaulting off of a ledge or sliding down a slide, they're going to assume that they're going to hit the ground with less impact or less force. And then when you initially do the math actually shows 64% of acceleration, which means it actually supports that they're hitting the ground with less force. And that's a paradox too. So it's like a paradox within a paradox. And yeah, I think just the levels of complexity is very interesting. All right, so let's show how they're going to hit the ground with the same impact. Physics equation for the kinematics, v squared final equals v naught squared plus 2ad, or 2 times acceleration times distance. In this case, I use g for gravity. We're going to have an initial velocity of 0 because they're just jumping off of something. This means v final squared equals 2 times gd, 2 times acceleration from gravity times distance. V final is the square root of the quantity 2 times g times d. That's for a free fall because we have full acceleration from gravity. Now let's see what happens if they pole vault down and they're following what's basically like a ramp that takes them down, but then that ramp spits them out vertical at 90 degrees to the ground. Bring down our 2 from our equation right here. Instead of having full acceleration from gravity, we're only going to have 2 over pi, or 64%, as I just showed. The distance they are traveling is 1/4 of the circumference. That circumference is 2 pi r, but in this case, I'm calling rd for distance, not diameter. So we see what cancels out here. We got 2 times 2 times 2 times pi right there, divided by 4 pi. The pi's will cancel. 2 of the 2's on top cancel. What we end up with is 2 times g times d. That equals v final squared. Take the square root of both sides. You get v final, our final velocity, of the square root of the quantity, 2 times g times d, or 2 times acceleration from gravity, times distance, which is identical to what you have up here if a person falls in free fall. So whether they are pole vaulting down or they are free falling, you get the exact same equation. And this distance that they travel right here, that could be 1 or it could be 3,027. And then gravity, it doesn't matter also, because as you can see with the way these coefficients or these numbers cancel out, g and d remain untouched. So this shows that if a person is pole vaulting, they will always hit the ground with the same velocity or same kinetic energy, which will be equal to the potential energy with which they started. All right, different ways to misinterpret this. This is a paradox within the paradox. If you have change in velocity over change in time equals acceleration, you could also say acceleration times time equals your velocity. We're going to have 64% of the acceleration, which makes it look like you're going to have 64% of the velocity when you hit the ground. But that's actually going to be stretched out over a longer time because that person's on the pole vault longer or they're on the slide longer. And this equation, 1/2 at squared equals distance. If you have 64% of acceleration in the y direction, it makes it look like you're jumping from 64% of the distance. Very fascinating because I actually got this wrong, and this is how I interpreted it. But the truth is, if a person's going down a slide or on a pole vault, they're going to be in the air for a longer period of time that will negate that 64% of the distance. So they're still hitting the ground with the full velocity, as if they jumped from the full height. Here's another misinterpretation. Mass times acceleration from gravity times distance equals your potential energy. And if you only have 64% of acceleration from gravity, it looks like you're going to have 64% of your potential energy. But again, that's negated by going out over a longer distance or falling over a longer distance. And I just showed an example here of a marble or something rolling down a hill. We always think of slides as being safer because they spit you out in the x direction. All that potential energy is turned into kinetic energy, and then it's burned off as you go through the friction of the air or the friction of the slide. But if you have a situation here where you're going down a tube, that marble goes down a tube and then it spits it out vertically right there, that marble will hit the ground with the same velocity as if it just had a free fall. Next page. I just made some quick notes here. Same final velocity as if you're falling from the same height. So falling on a pole, like pole vaulting, doesn't soften the blow. And this is because the important part, the area under the curve is 1. Area under the curve is 1, which means you have 100% of acceleration just spread out over a longer period of time. So you have same final velocity. In other words, your kinetic energy has to equal the potential energy, which is the height from which you fall. I also think it's interesting to be able to approach a problem from several different angles and really evaluate your thoughts to the fullest. So let's look at the time that the person will be in the air compared to a free fall. So if a person is pole vaulting, for how long will they be in the air compared to a free fall? Acceleration times time equals your final velocity. So you can say your final velocity divided by acceleration gives you your time. Our acceleration, our average acceleration, is 2 over pi. 1 divided by 2 over pi gives us pi over 2, which was the initial length across our x-axis. So that means our total time in the air will actually be pi over 2 times longer compared to free fall. This comes out to approximately 1.57 times longer, which means if a person is in free fall for 1 second, if they pole vault from that same height, they'll be in the air for 1.57 seconds. This proof right here, this logic, seems so simple that it actually seems naive. Like if somebody were to use it, it would lead them to get the wrong answer. The same way I got the wrong answer when I thought 64% acceleration meant that you're going to hit the ground as if you fell from 64% of the height. So I'm going to actually show another equation that shows that this is true, and that's the next page. I'm going to make this simple with simple numbers that cancel out easily. The distance from which you fall will be 10 meters. Acceleration will be gravity, but it'll be gravity times 2 over pi as your average acceleration. And I drew a little person here falling that's pole vaulting, and I call this the tipping equation. So if a ladder is tipping over, if they're pole vaulting, that's what this math will show right here. So your acceleration is 2 over pi times 10. That equals 20 over pi. Draw a box around it because it's kind of important. Now we take 1/2 at squared equals our distance. We know our distance is 10 meters. We have our acceleration as 20 over pi. Let's solve for time. That means time will equal the square root of pi. So that means that is for how long that person will be in the air if they are pole vaulting down off of a tall building or a tall ledge, or if they're on a ladder and the ladder tips over. They'll be in the air for the square root of pi as their time, if that height is 10 meters off the ground, which is about 30 feet. So that's a pretty significant fall. Now let's do free fall. So I showed a little person here, a ball just falling. Do the same thing, 1/2 at squared. Solve for t. We end up with the square root of 2. So a free fall means you'll be in the air. A free fall from 10 meters means you'll be in the air for a square root of 2 seconds. If you pole vault down, you'll be in the air for a square root of pi seconds. Let's compare the ratio of tipping compared to free fall. That's going to be the square root of pi over square root of 2. Square the quantity to get rid of your square root function, and you end up with pi over 2 times longer in the air, which is what I showed on the previous page. Pi over 2, which means you're in the air for 1.57 times longer. So very interesting problem, I think. I think it's a paradox that contains a bunch of smaller paradoxes. And understanding this really helps us understand the world and may prevent injury someday if we have a chance to pole vault off of a ledge or something because we think we're going to hit the ground with a softer impact. So I think this information is really useful to someone like myself that seems to like getting hurt and spends a lot of time in the woods climbing on things and jumping off of things. So I've done a bunch of videos that are related to this. You can see those if you're interested. I used the area under the curve in a video to find out how far away a shooter was as a bullet is slowing down after it's been shot. I also used area under the curve to get the water pressure on a wall or a dam. And I did some videos on paradoxes. You can see those if you're interested. I've done some videos on basic calc and trig as well. But in the trig video, I didn't cover the unit circle. I just kept it simple like triangles. So anyway, see those other videos if you're interested. And as always, this video is just part of my weird hobby or weird thought processes where I like to think about things and find answers. I guess it's not terribly weird though. Some people collect stamps and some people collect coins, and I collect math equations. So I try to keep all my videos just on original ideas or original thoughts that you typically won't find anywhere else. And they're kind of like the puzzles that I discovered and tried to figure out. So yeah, a lot of fun. So that's it.